Hello everyone, my name is Christine G and I'm going to be going over Module 12, which is on conditional probability and independence. And we're going to have different problems, and I'll put up a problem for you all to work on. And then in the top left survey, I'm going to have where you can put the answer in. So let's go ahead and get started with the first problem, and that will be good. Okay, so here you're just typing in the different formulas for the probability of A and B, and you can just type those into the upper left pole. These are for both independent and dependent events. Good question. And by the way, I don't know who writes what, so everything is anonymous in the answer box. Okay, I'm going to start writing these up. So they can be written a number of ways. I typically, there is the formula we all know and love, probability of A and B. And typically symbolizes multiplication, so this is the probability of A times the probability of B. And this is for independent events. And you could write it as the probability of B times probability of A, okay? And this formula only works for independent events. Now, there are other formulas that work for both dependent and independent events. So these work for both. So for the probability of A and B, this is equal to the probability of A times the probability of B given A. This is a conditional probability right here. As soon as you have something like this, a conditional probability, and they're asking you to find the probability of A and B, right away you should know, I need to use this formula. I can't use this one. So always, just in case, use this formula if you have some type of conditional probability. And then the other probability of A and B, the other conditional one would be the probability of B times the probability of A given B. Okay? And same idea here. If you're given this conditional probability, it's better to use this formula than to chance it that it's an independent event and that you could just say probability of A times probability of B. We're going to be using one of these conditional formulas on one of the problems in the later slides. So, okay, let's go ahead and I'll give you a minute to, 4 minutes to try and do this one. Or a minute, I'd say. There's no calculations on this one. Okay, this particular problem is just stating the family has 3 children already and they are all boys. What is the probability the next child is a boy? What's the probability on any birth that the child is a boy? It's always the same. It's always a half. This is an independent event. It doesn't matter if you had 10 children and they were all boys. The probability that the next one is a boy is going to be a half. It's not affected by the prior events. Okay? Let me know if anybody has questions on these. Or questions on that one. Any questions along the way, I'm happy to help. So go ahead and try this one. Good. Okay, let's take a look at this one. So we have a deck of 52 cards. Given that you draw a king for the first card, so let's look at the probability of drawing a first king, and that would be 4 out of 52 because there are 4 of each card in a regular deck. And then the probability of a second king, well, they don't replace the first one. So there are only 51 cards left, and there are only 3 of those are kings. So 3 out of 51. 3 divided by 51. Any questions on that? Oh, okay. All right, so let's take a look at the next problem. And we're going to be using one of the formulas that I mentioned on the first screen. So let me give you some time to think about that one. Okay, good. Let's go ahead and take a look at this one. And I had mentioned earlier, this is being recorded, so anyone's welcome to email us back and request this recording. So, and you can just do that off of the schedule that you get, the webinar schedule. You can just email us and ask for the recordings. So, okay, probability of A or B. This formula is equal to, or typically means add, so probability of A plus the probability of B, and then we're subtracting off the probability of A and B. Okay? So this is the formula. Right now we know the probability of A and we know the probability of B. This is what we don't know, and we have to figure that out. So in the beginning we had several formulas for the probability of A and B, and I mentioned that if you ever have a conditional probability, to be on the safe side you have to use that in your formula for the probability of A and B. So in this one we have we would do the probability of A times the probability of B given A. Why would we use that one? Because we have this, and so this formula would be the one that would work with it. So if we had this instead, then we would use a different formula, and I went over that one on the first screen. So here we're just going to substitute in the probability of A is 0.6 times the probability of B given A, that's 0.2, and then we have 0.12 for the probability of A and B. Now we can substitute in, we know, I should have left more room here. Let me try and do it up top. So we know that the probability of A is 0.6 plus the probability of B is 0.4, and then minus the probability of A and B, we know that's 0.12. So 0.6, this is like 60 cents and 40 cents. That's $1 minus 12 cents. So that would be 0.88. So this is the answer. This is the probability of A or B for this situation. I know that's a long one, but getting used to it, and maybe requesting the recording and following along with it, and you know, it's not too bad after you get used to doing that type of problem. Okay, any questions on that? Okay, let's try this one. Okay. Let's go ahead and take a look at this. So we have 6 purple, 4 green, and 3 yellow gumballs. And you randomly choose 2 gumballs without replacement. Given that the first gumball is purple, what is the probability the second gumball is green? Okay, so let's look at the first purple. And we know that there are 6 purple out of 13 total gumballs. And then they're asking us what is the probability the second one is green. They don't replace it, it's without replacement. So they take that one purple one out, and so they want to know the second is green. And we know that there are 4 green, and then there are only 12 left. So this would be 1/3 the probability. Okay? Questions on that? Or let me know if you have questions, I should say. Looks like someone is typing. Let me go back. No? Okay. Let me know. I'm happy to answer questions. So on these, you're just gonna we'll call these A, B, C, and D. And you could even, in the upper left box, you could just type in I for independent or D for dependent and type it in order of A, B, C, and D. That a try. Good. Okay, let's go ahead and go over these. So this first one, tossing a coin and rolling a die. Well, if the coin comes up heads or tails, it doesn't have any effect on the die. So that would be independent, definitely. And then let's look at the next one. Bag of marbles, choosing a red and a yellow without replacement. So this would be dependent because, and the key word here is without replacement. So once you pick the red one, the probability for picking the yellow changes. So it affects it, so these events are dependent. And then rolling a dice twice and getting an even number on the first roll and an even number on the second roll. Okay, so if you roll it even on the first one, it doesn't have any effect on whether it's an even number on the second roll. So these would be independent events. And then this last one, 2 dice are rolled and the dice sum to 8. Well, these are dependent events because if you first roll a 2, then it locks you in that you have to roll a 6. So the events depend on each other. So good. Good job on that. Okay. Now this one, and I typically do tree diagrams on this type of problem. I'm going to clear out the pole. Okay, good, good. So let's take a look. The first question is each birth independent or dependent? Well, every time you have you could either have a boy or a girl, and it's always half of the time you have a boy and the other half a girl. So the probability, it does not change at all. So these are independent events that occur in having children. And then here I'm gonna do a tree diagram. Ooh, let me see. It's not letting me erase, I don't think. Oh, maybe it will. So let me do it again. So here on the first birth, you're either going to have a boy or a girl. And then on the second birth, once you have a boy, you could have another boy or a girl. And then if you have a girl, you could still have a boy or a girl on the second round. And you notice I always put boy on top. I could have put girl on top. I just keep it consistent every time. And then here, boy, girl. This is the third birth. So this is the third birth. And so I can look at each of these branches. So the first outcome is all boys, or boy, boy, boy. And then the second one, I go boy, boy, girl. And then the third, so I did these two branches, and then I go here, boy, girl, boy. And then boy, girl, girl. And then I go down to, so I've done all these, and then I start on the girl, boy, boy. And then the next one is girl, boy, girl. And then girl, girl, boy, and then all girls. And you want to make sure you can read a tree diagram properly, and then that way you won't ever mess up on these types of problems. If you do it a different way, that's okay as long as you're getting it right. Fine with that. But you want to be careful, and this is a foolproof way to make sure you get your entire sample space. So the probability of getting boy, 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 well, that's only happening one way there. So 1 out of a total of 8. So, and then boy, girl, boy. So boy, girl, boy is different than boy, boy, girl. If you have a boy and then a girl's your middle child, it's definitely different than this. So there is, so let's look at what that would be. So boy, girl, boy. And that is right here, and that happens one way, so 1 out of 8. So these two events are equally likely. Good. All right, let me know if you have questions. So I'm going to keep moving and doing the recording. So, but here's another one that would be good. Okay, let's take a look at this one. So we have two types of diseases treated by medicine, type A and type B. And we have this table, and it's asking us to find the probability of A given B. So B is the condition. What I like to do is whatever is here is the condition. And so that's the only thing, the only area that we look at. And then it's asking us the probability of A given B. So the condition is, we total that out at 0.20, and the probability of A inside of B is, given the condition, is 0.14. Okay, and then what we do here is we say, okay, 0.14 divided by 0.20. We don't leave decimals and fractions, is 0.70. And then it's asking us if A and B are dependent or independent. Well, the way we know this is if we find the probability of A, and if that is equal to the probability of A given B. So basically what this means is that the probability of A, if these two are equal, the condition of B doesn't affect, the condition B doesn't affect the probability of A. It remains the same no matter what. So here we look for the probability of A, and for that we're looking at not just this this little area, but we're looking at the entire chart to get the probability of A. So let me erase that out. And so probability of A would be 0.70 out of 1. So 0.70 divided by 1 is 0.7. So the probability of A is 0.7, and that is equal to the probability of A given B, which is also 0.7 or 0.70. And these two, therefore, are independent events. Any questions on that? Let me erase that. Whoops. Okay. Oops, I didn't mean to do that. Okay. All right. And then let's take a look at this one. Okay, good. So I want to try and get through all of these slides for all of you and the recording. So here we have these different gumballs, and they're being chosen without replacement. So right away we know they are dependent events, because once you take one out, the probability of picking the next one changes. So here it's asking us to find the probability of pulling a purple and then another purple and a yellow. So and means we multiply here, and the probability of the first purple is 6 out of 13. And the probability, once we pull the first purple and then pulling a second one, would be 5 out of 12, because there are only 5 purple left and 12 total. And then the probability of yellow, well, there's 3 yellow out of 11 that are left because they picked 2 purple. And then we'd multiply this. 6 times 5 is 30, times 3 is 90. And then I calculated this out ahead of time. 17 16, so that would be 13 times 12 times 11, and then we could convert it to a decimal, 0.052. Okay? And on your test, you can have fractions or decimals, and it will be multiple choice. You can convert everything to decimals if that's easier for you. So their answers as well as your own. So, okay. Again, let me know if you have questions. I'm just going zipping right along. So. Okay, I'm gonna go ahead and start explaining this one. So first of all, I converted this to a decimal, 0.47, and this question is asking, what is the probability that the next 4 flowers randomly chosen will have at least one white flower? So here we know that the probability of the flower being white is 7/15. And we also know that either you're going to pick a white flower or not a white flower. So there are only 2 different outcomes that could possibly happen. Either you pick a white or not a white. So this adds up to 1 or 100% of the data. So, oh, I should have changed this over to, my eraser's not working, so let me change this to the decimal. So the decimal is 0.47, or typically means add, plus some number is equal to 1. Now what I can do to get this probability that it's not white is just take 1, or we can think of $1 and subtract 47 cents. And then we get the probability of it not being white is 0.53. So probability white 0.47, and then probability not white is 0.53. Okay, so the question asks, what is the probability that the next 4 flowers randomly chosen will have at least one white flower? So they're looking to find the probability at least one white out of the 4 flowers. So we know that either there's going to be at least one white chosen or no whites. One of those 2 things is going to happen. So they have to add to 1. Okay? Now, probability of at least one white is kind of tricky because you have to calculate first the probability of one white plus, then once you get that probability of two white, probability of 3 white, and probability of 4 white. And that's a lot of calculations. It's easier to calculate the probability that none are white, no whites. And we can do that. So here, I'm just going to rewrite this, at least one white, and that's what we're going to be looking for. But we can calculate the probability of no whites. So that would be probability of, oh, I didn't mean to do that, sorry. Let me just leave it like that. Equals the first one, the probability of it not being white would be 0.53, And so the first one not being white is 0.53, and the second one, and typically means multiply times 0.53 second, and the third not being white, and the fourth not being white. So this is third and fourth. So, and we can rewrite this. This is not 0.53 times 4. It's 0.53 to the fourth power. So now we can simplify that. 0.53 to the fourth power is equal to 0.079. So that's the probability of no whites on 4 picks. 0.079. So now we're still looking for the probability of at least one white. Well, we can easily get that now. We can just take 1 and subtract 0.079, and then we get 0.921. So the answer to the question, the probability at least one white, would be this 0.921. Okay? And this one, I think it takes time to process, so reviewing it, taking notes on it is a good way to go. So, and calling the math helpline if you have questions too. There's also one in the checkpoints like that. So, okay. This one, let me see. Since we're running out of time, I'm going to go ahead and do this one. There are a number of ways to do it, but what I'd like to do is a tree diagram because it makes sense, especially for visual learners. We have these 2 headache medicines, and that might cause insomnia, and 50% of the people who take drug A have insomnia, and 70% taking drug B have insomnia. And then it tells us 60% take drug A and 40% take drug B. Now this is key right here. If the person has insomnia, what is the probability that they are taking drug B? So this is the conditions we're looking for if the person has insomnia. So we're going to do a tree diagram, and we'll only look at the people that contracted insomnia. So, or that have insomnia. I guess you don't contract it. Anyway, so the first thing is that the person can be taking either drug A or drug B. And they take drug A 60% of the time and B 40%. So 0.60 and then 0.40. And notice these two, they have to add up to 1. Sorry about that. So here, then the next thing we know is that we have either they contract insomnia or they do not contract insomnia. So for drug A, it says 50% can have insomnia and 50% don't. I keep saying contract it, but I don't think that's right. And then for drug B, it says 70% taking drug B get insomnia, so 0.70, and then this has to add up to 1, so the other part of that would be 0.30. Now, if a person has insomnia, so this branch would count, and so would this. The other paths did not have insomnia. So we're only looking at, and we're looking for what is the probability they are taking drug B. So first of all, what we're going to look at is the total, because this is the same, this is like this is the condition insomnia, and that condition is going to go on the bottom of the fraction, that total. So taking, if they take medication A and they have insomnia, it's 0.60 times 0.50, which equals 0.30. Or the other way they can have insomnia is if they take medication B and contracted. So that'd be 0.40 times 0.70, which equals 0.28. So or typically means add, so we're going to add these two to get the total of insomnia. And this is the total number of people that have insomnia, I should say. So that that total amount is 0.58 or 58%. And then here we are looking for the probability that they are taking drug B. So taking drug B is over here. And so that would be 0.28 over 0.58, and then that is 0.48 when we simplify it. So I hope that makes sense. And then we have one last problem. Thanks for hanging in there, everybody, and for watching this if you're watching it. So, okay, this one, we've got these gumballs, and we don't know what the first gumball color is. What is the probability the second gumball is green? So let's go ahead, a tree diagram again. So first, let's say you choose two gumballs without replacement. So we can either choose purple or green. If we choose the purple one, the probability of having purple is 5 out of 7. And then for green, that is 2 out of 7. And that's the first pick. And then the second pick, again, they can choose either purple or green on either. And then here, once they chose a purple, they only have 4 purple left because they don't replace it. Since they don't replace it, they only have a total of 6. And then here, the number of green is 2 because they chose a purple first on this branch, and then 6 left. Then here, if they chose a green first, well, then they only have 6 gumballs left, but they have all the purple ones, so 5, 6. And then if they chose the green first, and then the probability of choosing another green, well, there's only 1 other green left out of 6. And then the question's asking, what is the probability the second gumball is green? Well, we have 2 branches where that's going on, right here and then right here. So what we're going to do now is look at the probability that either this or this occurred. So let's write it. So either probability of purple-green, which is 5/7 times 2/6, or probability of green and green, and that's 2/7 times 1/6. So or means that we're going to be adding these, and then 5 times 2 is 10, and 7 times 6 is 42. And then here we have 2 times 1 is 2, and then 7 times 6 is 42. So this would be 12 out of 42, which is equal to 2/7. So that is the probability that the second gumball is green. Phew, any questions on that? I just went through it really quickly, so I appreciate everybody watching. I'm going to go ahead and stop the recording, and please request more videos if you need them.